with that, I would like to welcome all of you to our workshop, HARMLESS workshop. HARMLESS is an EU-funded project which works on safe and sustainable by design for products put forward by industry, including advanced materials. And in this presentation and workshop, we would like to introduce you to one of the key elements of this project, which is the user-friendly harmless decision support system, which helps you understand which of the materials is more or less hazard or sustainable. We will present that and demonstrate this in the context of a case study, which we have conducted within this project. Just a few words on the consortium. So we have a overall active time of more than 4 years. The project will end 1st of February 2025. We have 20 partners from 12 EU countries, 2 industry partners, large industry partners, and 4 SMEs, which are highlighted here by the red boxes. Chalmers, Industrietechnik, Thema Solutions, Idea Consult, and Misfig. And it's coordinated by the Helmholtz Center Munich, namely by myself and my colleague Tobias Stöger. Just to give a little bit of motivation why we're doing what we're doing, you may be aware that the European Commission announced the Green Deal in February 2023. As part of this, there was an EU action plan towards a zero pollution for air, water, and soil put in place. There's also a circular economy action plan now active, and there's an EU chemical strategy for sustainability towards a toxic-free environment. And this is all geared towards coming up with a pre-market approach to chemicals. So before they get released, actually, to conduct surveys and optimize the procedure to hopefully avoid large volumes of chemicals and also avoid using chemical properties which may be harmful to human health and the environment. Now, this concept is going to be extended in some ways towards advanced materials, so going away from just chemicals to advanced materials. And this is what this topic is about, of course, here. So just a little bit of what do we mean by advanced materials? There's no official definition yet. So we are using the wording which was proposed by the OECD Working Party on Manufactured Nanomaterials. And they talk about rationally designed materials, so not accidentally occurring materials, rationally designed materials with new or enhanced properties, and or targeted or enhanced structural features to achieve specific or improved functional performance. So just to keep that in mind, so this is not a specific category, a type of material, it's more from the functionality of the material, the definition or the wording. I'm sure many of you are aware of this stage gate process in terms of product development. In industry, of course, you always start with the product idea and you do some initial screening. Then you go into the lab and analyze further the suitability of the product towards the overall goals. And then you go into the pilot scale and then eventually you launch this product. And in the very first phases, very often, not always, yeah, but very often one focuses on functionality and cost. And then at later time points, you worry about risk issues or regulation concerns and possibly, of course, sustainability as well, which is also part of cost. So now with the project we are working on, we are trying to adapt this concept so that you can include risk and regulation sustainability also very early in the product ideation phase as well as in later time points. So throughout the entire product development scene, we hope that the tool we can present to you today will help and facilitate functionality, cost, risk, sustainability considerations all at the same time. And of course, this is a pre-market approach again, and this is not on a regulatory level right now. It's just as a tool for industry to work towards less volume, less harmful materials to be released. So in terms of value, what could be in store for you as a company? Of course, if you consider safety and sustainability during all phases of product development, you may mitigate the health risks for your employees, but also for consumers and the environment. There's a potential that this product then receives a higher acceptance at the marketplace, specifically with relation to sustainability. This is quite vogue right now. And of course, it's also a money issue. So if you invest in a product which later potentially is considered non-safe or non-sustainable and may have to be withdrawn or is not so successful in the marketplace, you may have to either withdraw completely or you have to redesign the product, incurring additional costs. And in the long run, probably there will also be some regulatory acceptance issues, but this is not at hand right now. So very briefly, what is the concept of harmless? We developed this safe and sustainable by design approach for advanced materials to be included in products. It's a stage-gated process so that it's seamless integrated into industry processes. We validate this with case studies, real-world industry case studies, and come up with a validated, user-friendly, safe and sustainable by design tool. This is what we will talk about today. There's two other arms leading into that. First of all, we're establishing data-rich environments for the materials of interest. So we do some data gap filling, and we also provide high throughput screening, and we develop non-animal based testing methods, the so-called new approach methodologies in all relevant aspects with respect to hazard exposure, internal dose, life cycle analysis, as well as ecotoxicology. And the second arm is that we have a strong in vivo anchorage. So we're not just doing in vitro in silico new approach methodologies, but we also try to look for hazard markers on the in vivo level with animal models and try to stratify them into different modes of action and adverse outcome pathways. So again, this we do on the human health level and on the ecotoxicology level. And last but not least, we have, of course, a strong database called eNanoMapper. And with this data hub, we not only collect data and we have tools to implement data seamless from the internet with AI-driven approaches, we also have multi-scale modeling integrated to some preliminary analysis of the data right at the eNanoMapper level. And then, of course, we are striving to have a strong in vitro, in vivo translation in terms of hazard assessment. And last but not least, everything should then be combined in the positioning of the advanced material in the risk and sustainability matrix. Yeah, we had 5 case studies we considered from 5 different sectors. You can see them here. So we have paper making, paint formulation, we have catalysts, we have a facade insulation case study as well as agricultural application. Without going into detail, I just want to make you aware that we focused on mixtures of metals or metal oxides, and we had high aspect ratio nanomaterials, so elongated or fiber-like materials, which are of particular concern in this context. Today, so you see that all of these materials have either mixtures of metal oxides or are hard. Today, we will then focus on the catalyst case study, perovskites, which will be introduced in detail in just a minute, so I won't spend time on this. The objectives for today are that we want to demonstrate this user-friendly harmless decision support system for you, and we want to find out whether and how this work of us can work for you as SMEs, but also as other people joining the workshop today. Yeah, with this in mind, let's have a look at the agenda. So first we will have this overview of the approach, the harmless approach to safe and sustainable by design, which will be presented by Blanca Suarez from Temasol. Then we'll give you an introduction on the perovskite case study. This will be done by Veronica Di Battista from BASF. And after that, you receive an introduction to the Harmless Decision Support System from Eugene von Sommeren from TNO. And that will be followed up with a demonstration of this decision support system by Susan Deckers, also from TNO. And then we hope we have a very lively interaction with you in terms of questions and answers and hands-on experience and some surprise activities. Yeah, with this, I would welcome Blanca to take over and give us the introduction into the harmless, safe, and sustainable by design approach.
Thank you, Otmar. Trying to share now the screen. Sorry, going into presentation mode. Okay. So, did you see my screen now?
But not in the presentation mode yet.
Not
yeah,
yet.
now
Maybe
we
it's
are.
a bit slow.
Yeah,
Is that
now
right?
it's there.
Okay. So yeah, it is my pleasure to introduce the harmless approach to safe and sustainable by design. I'm going to present now our safe and sustainable by design framework, which represent the concept where our decision support system was built on. So it's a little bit of background. So first of all, I wanted to highlight that safe and sustainable by design is not going to be a regulation, and it's not regulation, but it's a recommendation that came from the European Commission to perform research and development activities. This recommendation came up, you can see here on the right of the screen, in December 2022, where they do recommend to implement safe and sustainable by design in research activities. This recommendation is also supported by several documents that the JRC has already published on the safe and sustainable by design framework, then the identification of criteria and the outcome of different case studies. And we also we are working on the ASCEN standard. This ASCEN is the European mirror of ISO, where we try to develop a document which is useful for industry and which will help them implement safe and sustainable by design. And this document is ongoing and should be ready for round robin around different member states for comments next year, next June 25. So together with this, also different industry associations have also produced some publications on their thoughts on how to implement safe and sustainable by design. And you can see here on the left of the screen, this is a publication, very recent publication from the CEFIC, which is the Chemicals Association in Europe. This is March Sustainable by Design currently supporting documents as well. I also wanted to say that sustainability is not new to industry. It's been used since the late 70s. And they have been working on different documents internally to help them streamline when they are developing different leads of products, which ones should go ahead along the innovation pipeline. So these are different strategies that industry have implemented in-house, and they don't necessarily open them to the outside world, but we know that they are there and they are working towards the implementation of more sustainable solutions addressing the different sustainability goals from the UN. So this is also already available and it's not new. Now, this was a slide that was already introduced by Otmar, but what we wanted to say, we identify a market need, we look at functionality and regulatory issues, and sustainability was performed towards the end of the innovation, perhaps through an LCA. The LCA is really data demanding, and at this stage when one performs LCA, and it's too late to change your innovation. You're already at the end, you're already close to market launch. So one of the ideas to help companies achieve a more successful rate on product launch is to try to anticipate regulatory issues earlier at the development stage. So we don't find ourselves at the late stages where we see that one of our material is not regulatory compliant and we have to start all over again. So one of the ideas of safe and sustainable by design is also to help industry achieve regulatory compliance in a cost-efficient way as well. So for this, we have like Otmar mentioned before, we have the stage gate model, which in Harmless, we have reduced it to 3 stages, product idea and screening, the lab scale, and the pilot. And we have selected different methodologies which have different data demands along the innovation process. So we can already anticipate earlier if there are issues rather than leaving them towards the end. So in Harmless, we are looking at modeling tools earlier in the product development. At the lab scale, we are looking at acellular assays, those in chemical assays, which one in cell grown in culture. And towards the end of our innovation, we will suggest more cell-based assays, which provide more quantitative assessment, but they are also more expensive. And as I said before, one of the ideas is to anticipate regulatory demands already earlier by predictive methodologies that can tell us if we'll have some issues later on towards the end of the process. So this is the harmless, safe, and sustainable by design framework in a nutshell. So maybe this slide has too much data, but I'll just take you through it quickly. So the main point is that our framework is divided into 3 stages, as I said before: ideation and business case, laboratory phase, and pilot. And we have a pre-stage, which we call here the tier 0, which is represented by the AMIA tool. AMIA stands for Advanced Materials Earliest Assessment. And this tool is very simple and it only will tell us if what we have is really an advanced material and can be run through our framework. So once we go through this initial tool, we have the 3 different stages. And each stage is composed of 2 main modules. The yellow module you see here regards safety, and the green module regards sustainability. And we always have a gray module which indicates performance, which actually we haven't seen this one in the ERC framework for now, but we have included it, of course, in our assessments. So regarding safety, we will look at intrinsic safety, safety during production, manufacturing and end of life, and safety during use. And regarding environment, we have looked at environmental sustainability during production and manufacturing, and also during use and end of life. And for these different modules, we have selected different tools. Like I mentioned before, they have different data demands depending where we are along the innovation process. We have also produced design principles to help innovators put together the ideas along the value chain, along the innovation process, and to help them implement safe and sustainable by design. So all this concept has been realized now into the decision support system that Eugene and Susan will introduce later. So just to end my presentation, to say that the safe and sustainable by design can help us select the most appropriate tools. You can see here on the left of this the slide, many different cost-efficient tools to address the same endpoints. So with this, we have actually put together what you see on the right, which is our harmless decision support system, which have been compiled following what I just explained, and different modules will compose of different data demanding approaches. So we will start with the tier 0, which is the AMIA, which has 3 questions. We will continue with the ideation phase, which will be represented by the WAS module, which will have 14 questions. And finally, we have the laboratory phase represented by the ASI module, which will contain actually proper measure descriptors. And we are still working on the pilot module, which is work in progress. And with this introduction, I will leave the floor to my colleague Veronica to introduce the case study. Thank you.
All right, I'm going to share my screen. All right, can you see my screen?
Yes, Veronica, but it is not yet
It's
in
not
presentation mode. Yeah, perfect.
Is it yes? Okay, perfect. So thank you, Blanca. And now I will follow up on what Otmar's presented. So I will introduce you the case study we are going to look into today. This is one of the case study we are looking into in HARMLESS, and it is their perovskites as components in three-way catalysts. So I'm going to introduce you this case study by looking into three important things of every innovation project. So this is a design space, and with design space we mean all the physical-chemical properties that actually have an impact on the performance, so on the function of your material. Then the functionality, of course, and any issues or concern that may be related to the components that are in the materials that you are synthesizing. So with respect to the design space, these perovskites, so they are oxide perovskites, first of all, and the parameters, what is really important in order to make them, what can be tailored to make them more performant, is their composition, the crystallinity, the size, and the surface area. So these properties further influence some electronic properties as these materials are semiconductors. So for example, their conduction, valence band level, and their band gap. So to say that this is specific for these perovskites, and what is important to understand what will follow up is just that we have here several versions which have been varied with respect to their nickel and cobalt content, and with respect to doping of palladium or platinum, because it's important for catalysts in order to enhance their catalytic activity. And then with respect to their crystallinity, they are crystalline materials, and all these perovskites are AbO3, have a crystal structure AbO3, and in A we always have the lanthanum, and then in B position we always have or cobalt or nickel in this pseudo-cubic crystal structure, which of course depends also on the temperature you're at. And then also important is their size and surface area. So when we look at the images, but also at the numbers here, we understand that they are not actually nano by rich definition, but their size and their properties are actually enabled by their close to nano size, and so they would be nano-enabled materials by ISO definition. And then it comes to their functionality. So all these properties enable their functionality as three-way catalysts. So as I said, they are just components which really enable and improve their function as catalysts. And here in the video, you can see that the main target for them is to basically convert pollutants like carbon monoxide or NOx into less harmful chemicals like water and nitrogen and so on. And so this small amount of catalyst of perovskite enhances
Donald Trump a long time ago. You're the one who needs to disentangle from that situation. And I will tell you this.
Okay, so they enhance the catalyst turnover activity and increase the total oxygen storage capacity. Also, in HARMLESS, we look at the sustainability also connected to the performance, because often an increase in functionality also is strictly connected to, for example, a sustainability goal, as in this case. So a better performing catalyst will also contribute to Sustainable Development Goal 11, so improving the air quality with a high performance catalyst. And then, yeah, this is great, but of course, so we have mentioned cobalt, nickel, so there might be some issues and concerns that has to be taken into account, and we want to balance all these dimensions, so the sustainability, the performance, but also any risk. So we know that I said that they contain cobalt and nickel, which are both regulated anti-CLP as non-carcinogen, so we should look into this. They're also multi-component, and so might be that mixture effects come in, so we should look into this as well. And for the sustainability point of view, all these metals are also known as critical raw materials, and this can also be a reputational risk, and so this can also be doesn't have to be overlooked. And with this, I give the word to Eugene, and yeah.
Thank you, Veronica. I will give an introduction to the Harmless Decision Support System. Can you see my slides? Yeah. So the goal of our task is to build a user-friendly decision support system, but then based on the safe and sustainable by design framework developed in Work Package 4, as explained earlier. And we try to build a tool for companies, including small, medium enterprises, but also their consultants that are working on with innovative products and using innovative materials in helping them choosing the right nanomaterial in a way that it is designed in a safe and sustainable way early in the process. So although the tooling works for all nanomaterials, within Harmless we focus mostly on high aspect ratio nanomaterials and also multi-component nanomaterials. And we understand that as a company you are going through all the different innovation stages from idea to launch, and we want to help you in all these different stages and also take into account the different life cycle stages of the product that you're working on. So that means for us that we want to combine all the knowledge and models and data developed within Harmless, but in a way that we create a decision support system where you as a user can really work and use the tools and not just be a referral system that refers you to other sources. So we want to create a support system where you can do your own analysis and fill in the answers and run the tools and get answers directly in the system. If you look at Harmless as a project, not visible today, but there's a lot of work being performed in other work packages in investigating and developing different NAMs. And of course, that creates an enormous amount of information and data on all these different nanomaterials that we are measuring with all the different NAMs. But also people are working on based on simpler studies. But also we learn a lot about all these different experiments, and that knowledge and all these insights, that's also useful for creating a decision support system. So all these elements come together in the safe and sustainable by design framework, and of course also taking into account all the different external initiatives like the JSA and the Gracious Blueprints. And within the framework, we are able to decide which models and which methods and which assays work best in which situation. But if you look at it from a technical point of view, we decided to capture all the Harmless data on all the different nanomaterials in one central database called eNanoMapper, which is a database that has already captured other nanomaterial measurements from a lot of other different nanomaterial studies and projects. But we also want to do the same thing for the knowledge and the model. So we created a model fair point where we can capture all the different models and are able to run the models and see the results. And also try to capture the knowledge and insights into a fair data point where we can capture the information gathered in the project. If you look at that, then the decision support system is basically a smart layer on top of these elements, where the user provides information about the project they're working with. And based on that, the decision support system can smartly decide which data or which knowledge or which model is useful in that situation and provides support to the user back based on the information that the user has provided. Well, on the knowledge and the data being generated within the project, they can be used to create mathematical models. Models that say something about a certain aspect of your project, for instance, something about inflammation or something else. And we realized that if you are able to make this process efficient in turning those models into tools in the same platform, that would be very useful. So we make it possible for mathematical models to be turned into tools by just adding questions and a result page and then make them into a digital tool available to the system. But that would mean that the decision support system doesn't have to code in all these different models being generated in a hard-coded way. But if you can make a decision support system that can use any tool that has been added to the list, then we can make it very useful and efficient. So the decision support system has an action recommender that knows about all the different tools and also knows about the situation of the user. And based on that, it can recommend which actions or which tools are useful at that situation. The user can then decide to run one of those tools and in that way provide information to the system and also gets in return advice and insight in their situation. And basically what you see here is that there's a loop going on here. So you do one loop where you run a certain tool, then the information changes, and based on that, other actions can be recommended. Well, building it in that way also makes us available to say for some tools, they might be useful to create as a standalone tool. So that users might also use them independent from the decision support system. And we will see an example in the form of AMEA later on in this workshop. Okay, this sounds a bit abstract perhaps, but if you look back to the safe and sustainable by design approach and the different stages that have been defined within our framework, we want to focus on the three earlier phases. Ideation and business case, there you want to have considerations, you have just an idea, you want to know, you want to get warned of early issues that you want to take care of, and you want to get guidance on how to design your nanomaterials in a safe and sustainable way. When you are ready to go to the lab phase, then it's more about the different materials that you have created. You want to compare them and see which is the best nanomaterial for your situation. And when you go to the next phase, in the pilot phase, you have chosen one of your safe by design versions, and you want to more intensively assess that safe by design version and understand what the consequences are before you scale up to actual production. And you see that when you start in the beginning, you have little information, and the further you go, you want to invest a bit more, and you also have more information. So in terms of the decision support system, we start on the left mostly with simple questions that are easily answered in that phase where you're still thinking about your design, based on questionnaires and hazard banding approaches, for instance. In the lab phase, we're switched to more measurements, for instance, more acellular assays, and you want to compare the measurements between the different safe by design versions. And in the pilot phase, you go to more in-depth measurements, but also try to combine the different measurements into more advanced predictions, and also more advanced tooling that might be more difficult to handle while you're still in the beginning. So we realized that most of the tools out there are really quite difficult to be used. And so that's why we wanted to focus on the two earlier phases. And we created three different tools: AMEA, WASP, and ASDI, especially tuned to that earlier phases. So when you start with a project in the decision support system, and you follow the recommended workflow of HARMLESS, then we recommend you to use AMEA, which are just three simple questions, and based on that you get a category of your products, and also get already some advice based on the design principles that you can handle in order to come up with a nanomaterial that is safe already. And it also helps you decide whether or not it's useful to continue with the decision support system. And then we tried to use the best questions from a combination of all different tools and initiatives, and created WASP, where with only 14 questions that are easily answerable, you get already an idea on early warning flags, things that you have to take into account. You get more specific design advice and also assessment advice, so advice on what assays and measurements you should do when you go to the lab phase. So in the lab phase, there you have your different nanomaterials that you want to compare. So you create your different advanced materials, and you want to compare them with your conventional materials, and you start using cellular measurements and want to a visualization where you can compare those different designs. And when you're ready with that phase and you've decided on one nanomaterial, on one design, then you're ready for the pilot phase, and then you can use more advanced measurements and more complex tools. And Suzanne will show, for instance, one of the Bayesian network tools that we have developed. But that's for later. So how does the decision support system guide you through this workflow? Well, the idea is that when you start a project, then you start in the project dashboard. And there, for each of the actions, for each of the tools, we have developed a colored tile and recommending you which tools or actions are best for you at this current situation. Then you can decide to run one of the tools, and you basically are adding then more information to the system, and you get in return some textual advice or a visualization that gives you more insight in your current situation. And based on that, you come back to the project dashboard and new actions become more relevant for your current situation. So you go through a cycle where you continue to use the DSS over time and while you progress your design during the different innovation stages. So here's an example on how the recommended actions are shown. So in purple, we show the 4 most recommended actions for you at this early stage. But you also see at the bottom in brown that there are lots of other tools and actions that you can take, but they are still optional. We don't think that they are relevant for you at this moment. But as a user, you don't have to follow our workflow. You're free to experiment also with the other options in the system. But that's, of course, for a more experienced user. If you're a user that starts, we recommend you just to follow the recommended workflows with the purple tiles. So for each action, we try to, of course, explain what it does, but also say something about the difficulty of using that tool, how long it takes to run the tool, and in which stage of innovation that tool is most relevant. Now, just let me explain how that then would work for this AMEA, for one of the first steps in the workflow. You click on the tile, then you get into explanation pages that explain you a bit about the tool and the background. Then you have a phase where you can fill in information and provide and give answers to the questions being asked there. And based on that, you get an advice page in the result that will give you advice on the situation that you have provided to the system. And based on that, you can go back and you can run a different tool. Now, I hope that you are eager to know a bit more on which questions and what advice you would get. But Suzanne will present that in the next presentation. I will stop here explaining the DSS and show a little bit about how to access the system. So not now, but later after the workshop, you can follow these instructions. So we decided to create all the tools on TNO's Diamonds platform. That's a platform that's sustainable for many years. It has already existed before Harmless, but also will exist for many years after Harmless. And this is a way for us to make all the tools that we develop sustainable for a long term. But as a user, you can go to diamonds.tno.nl, you can press on the login button, and in the bottom right, you can click on register a new account. If you then follow a few of the activation steps, then you get access to the platform, to the tools that have been made publicly available. For instance, the tools that have been made before Harmless, like ACell and Licare Nanoscan and HotScan. But of course, we are developing tools within Harmless, and our partners have access already to the tools that we are developing. And we invite you all, if you want to collaborate with us, we can provide you already early access and already see if we can help you with your use case by using the tools that we are still developing before we have made them publicly available. So if you want to collaborate with us, then we can give you already early access and you can help in the development of our tools. So AMEA is one of the examples of a tool that we have created as a standalone tool, and you will experience it later in the interactive session after the presentation of Suzanne. So you can play around with that, but it will also become available soon as one of the public tools. But of course, the decision support system is still being developed and will only be available next year, early 2025, unless of course you collaborate with us. So I want to finish up. If you just register a normal public account, you will see at the bottom the publicly available tools. AMEA is a standalone tool that we cannot play with later on in the interactive session, but will become soon publicly available. And the decision support system, of course, is available if you collaborate with us, and we are heavily developing it at this moment. So to just recap, I've shown you a bit of the generic principles behind the harmless decision support system. We try to make it a fair and a modular approach and an efficient way to create tools into a decision support system. And I've also shown you that there's a guide, we guide the user in a workflow through the different innovation stages. I've shown you that you already can get access to the public tools, and soon AMEA will be available for you to work as well. But a decision support system will become available early next year. And of course, later on today, we'll get a sneak peek of AMEA. And hopefully you're eager to know a bit more about the actual contents and actual questions in the decision support system. And for that, I want to give the floor to Suzanne.
Thank you. Sorry about that. Just trying to get it in presentation mode. There it is. So for the demonstration, I start again with the workflow. I'm not going to explain the workflow again because it's been explained by Jen and also already introduced by Blanca. So we start with a new project, the perovskites, and we start with AMEA, a tool which will be in the upper left part when you enter the tool. And it consists of 3 questions. So we are going to take back the first presentation from Veronica in our mind. We have the perovskites as a catalyst, and we will just go through AMEA answering these 3 questions. So the first question will look like this. Does it contain or consist of particles? And you have 3 options, as you can see in the bottom of the slide. Either it consists of particle, it contains particle, or it doesn't consist or contain particles. So in the case of the perovskites, it consists of particles. So it's a powder or a suspension, and in this purpose, it's a suspension. So yeah, you would tick the first button and continue. So in the next stage, you have a couple of questions, or no, you have just one question saying, is it a nanomaterial or is it nano-enabled? We have some explanation. I'm not going to read it all, but it really, you have to look in what is your region that you want to make your material applicable, and look at the definition of the regulatory definitions for nano and nano-enabled products. So you have REACH and you have ISO, and in this part, it's we have ticked the box because it's both according to REACH and ISO. It's a yes. It's a nano containing nano materials and nano enabled. So then the next question, is it an advanced material? So this is also always quite nicely to discuss. You have the OECD description of advanced materials, which is the bottom part, the upper part of my slide. You have the AMI, who has described advanced materials, and in our own project we have added a little bit more specific to make a distinction between conventional. So yeah, when is it really new? And we thought that we have decided that, all right, it's not conventional if it's less than a decade on the market by several suppliers in tonnage scale. Well, in this case, it's an advanced material, so I would answer yes. So if you go through the tool, and now it's not, sorry about that. Yeah. You'll get the categorization of your material. So in this in this example, it consists of particles. It's nano-enabled and it's advanced. So it's in this category, and consequently, because our decision support system focuses on advanced nanomaterials, we are right in the alley of our applicability domain. Well, that's a result, but it also comes with an advice. So not only your category, but also an advice. And for that, you can click in which innovation stage you are. So, well, starting from the first stage, idea, discovery, and scoping. So you click on that, and you have your category, and you get a big advice page. I'm not expecting you to read this all, so I made an enlargement here. So it gives you advice, for example, what to look into in this phase, what characteristics. So at the bottom, there's the characteristics of your innovation stage. And it tells you a little bit what to look for, what are the design principles with respect to exposure, hazard, and sustainability. It also gives you guidance, design principles that are more focused. So consider the end of life, for example, or consider a design for circularity. All these aspects are included there. Also a little bit more specific. This is a whole sheet with a whole lot of information, so it's written out a little bit more. If I take one of these in the middle, then if your material's a multi-component, which is the case in our perovskite example, you have to make sure that transformation might become relevant, and you should characterize the release or the released forms throughout the whole life cycle of your product. So have a look at that. Well, in the contents of time, I'm just wondering if you, no, I'm not blocking anything. So then once you decide and you categorize and you decide you can continue within the decision support system of HARMLESS, you enter the product ID screening phase. And we developed, as Eugène already told us, the WASP 14 questions to start off with. So that's here. So you click on WASP. And you'll go into those. So WASP is designed basically to raise flags, to identify hotspots or concerns in the early phases, but also to give you some advice on how to design or redesign your material and how to further assess it if you decide to continue. So WASP has 14 questions. There's basically in 3 categories. So first the exposure, then the hazard, and then a third, some safety aspects. So when you start with exposure, for example, for particles, it's very important if you work with a powder or if dust or aerosols can be released, which can be released to the environment, but also human exposure might occur via inhalation. So that will be the first question. And in this respect, we would say yes. For the perovskites, that would be a yes. So is consumer exposure foreseen? Do you expect, for example, that it will be used in a consumer product, or can it be indirectly? Can there be indirect exposure for consumers? For example, if you look into pesticide residues on food materials. And then the third question is, in which life cycle stage is occupational exposure likely to occur? And these questions, they trigger certain advice. So I'm not going to go through all the 14 questions. And now I'm going to go to the result page, and then you can click For example, I answered the first question, is the material in powder form or can it release dust or aerosols? And I ticked the box with the yes. The answer is a yes, which would mean that here with the design advice, it gives the reasoning behind this yellow point of attention. So inhalation exposure is likely, and it also gives already a design advice. Here it's very simple to avoid this, use, for example, liquids or dispersions. And then it continues with assessment advice. So for this particular trigger, we used the inhalation IATA by another EU project, Gracious, and a tiered assessment, and it automatically gives you advice on what kind of aspects to consider in the next stage, and that's on the right side of this slide. So that are default or potential descriptors you can look into when you continue to the next stage. So then taking this into the next stage, the focus will be that you have a couple of designs, so several safe by design versions, which you would like to select the most important or the most optimal one, considering the different safety and sustainability aspects. So for this, we developed the alternative safe by design design inspector, or ASDI. And when we click on that, we enter the lab phase and we're going to compare our different materials. So starting off, you fill in a matrix, and this is why I'm not going to do a live version, because it's you will generate some data. But first of all, you start to define your different versions. So where do they differ? What's the design space? So in the case of the perovskites, they differ in size, surface area, and chemical composition. And then you also identify your conventional material. So what is another material that is comparable that is used now? And sometimes it might be useful to have some reference materials there as well. These are materials for which we have a lot of information, for example, on one of these aspects that can be useful for comparison. So these properties are entered first in the matrix, and then you continue to select from a default list of relevant descriptors, those descriptors that you think that might be, oh, sorry, there's something, that are useful for you and that you can test. And these are basically the information and acellular tests. So it's not a full assessment or safety assessment yet. So for example, it's dissolution in relevant media. So for human health safety, it's in lung lining fluid or lysosomal fluid, testing the dissolution. So you fill in the these parameters, for example, the size, surface area for each of these safe by design versions, so the ATMA materials, but also for the conventional material and for the reference material. So then the results. So based on that, you also have defined your biological relevant range with that, with each of the descriptors. And then the system will come up with a coloring, a continuous coloring from green to very dark green to a very dark red. And it gives you here, for example, the bottom part has a lot of lines on them. So each of these lines is actually depicting one of the descriptors. And if you click, for example, on this whole dimension of human safety in the occupational one, you will get into a more detailed description of each of the descriptors. So that is basically when we click on it, you will see a sheet like this. I've now entered only these, the size, the surface area, and 2 chemical compositions which were relevant for a hazard assessment, because these are metals that are toxic to humans or the environment. So here you can see, and based on this matrix or the results of this, you can have a look and compare both each of these 6 materials, safe by design versions, which you have developed, to the conventional material, which is the CO2, and also to some reference materials on the far right side. And from this, you can select the most optimal one. So you do an overall assessment, and we didn't aggregate all these little criteria into or descriptors into one, but that from looking at the differences between the different versions and also looking at your design space, you can also try to change something to make an improvement. And in this evaluation, we saw that there are limited differences between the different perovskites, but more relevant differences were observed between the perovskites and the reference material, for example. And we also saw that increased nickel content correlates what's to be expected with the hazard potential, but that doping with palladium tends to decrease the toxic potential and increase the performance. So the suggestion would be here, based on this matrix, to take the one of these versions, so that's the Laconi PD, into the next stage, because it has a low nickel content, and palladium also reduces the potency and increases the performance. So knowing that, we take that one safe by design version to the pilot scale. And in the pilot scale, we want to become more quantitative. So this is work we're still working on. Of course, there are existing tools in, we enter the pilot phase, and we assess our picked ones. And so we have, within HARMLESS, we have, for example, one of the tools is a Bayesian network. But first, this is what I wanted to show first. Sorry about that. So in the pilot phase, we go into more complex models. We do cellular in vitro tests, and we also combine different information into more complex predictive exposure and hazard models. On the sustainability side, we look into semi-quantitative target indicators, which are in the sustainability developmental goals. And we try to visualize this, normalizing the scores of each of these safe by design aspects, whether it's been on health risk, environmental risk, or sustainability, and also including an uncertainty range, because here we're trying to become more quantitative in our assessment. So there are already existing tools that we might include in the decision support system, which we can run and then couple and get the results into these visualizations. You can also look into release testing and in vitro toxicity testing, ecotoxicity testing, for example, and this all will be combined together. Also within HARMLESS, there's a lot of data generated, a lot of in silico, in chemical and in vitro, and also some in vivo information, which are now currently being exploited to build predictive hazard modeling, especially on human inhalation. So it's using AOPs and in vivo anchoring to try to predict human health endpoints. Well, one of the big data sets we have is on one of the most critical effects in animal experiments with inhalation of particles, and that's predicting the neutrophil influx. So using the physical chemical data of the material and the in-chemical one, and sometimes also in vitro data, there's several statistical machine learning and AI methods that we're currently using to see if we can build predictive modeling with the data set. One of these predictive models, an example, is the Bayesian network model that predicts the neutrophil influx. And here you see the different input parameters which the model will use. In vitro assays is in yellow, and there's a model built with and without this. So we tried also to look into what is more predictive. So here are some statistics on the performance of the different models. So we compared the Bayesian model that I showed you also with some other statistical models like a random forest, decision tree models, and in red are the ones that perform the best. So we try to already put this model into a tooling. So we built, like Eugène explained, from this model, we built a digital tool which answers a couple of questions, starting with dimensions, and then moving, like is shown in this sheet, moving on to nanomaterial measurements, acellular loss production, dissolution rate, and release of toxic metals. And then finally, optional, you can also put some in vitro data in there. And then this is still a first screen. It's a prediction comes out. Actually, here what you see is a comparison of the control, which is doesn't contain any particles, carbon black, which is often used and tested in vivo assays alongside your own material. And here I entered the perovskites parameter. So here's a prediction of the perovskites, what perovskites would neutrophil influx in vivo would be in the lungs or in the lavage fluids from the lungs. So that's just a sneak peek, because especially this last pilot phase of the decision support system is still under development. Some key points, what we still keep into mind is we want to keep it still easy to use in all innovation stages. Well, of course, we follow these different innovation stages and we have a different tools, starting from very limited data to more comprehensive data and models in the later innovation stages, and including uncertainty there as well. And we use then existing but also newly generated data and models, and we try to integrate the data and the knowledge and the models to reduce the amount of questions that the user has to answer, to characterize uncertainty, and to also handle missing data. I think for now I will stop talking and see if there's any questions here.
Well, thank you very much, Susan. So at this point, we agreed that we would stop the recording.